Log4j Architecture. Here you can see the classes which is used by the Log4j here. Apache Log4j is a Java-based logging utility originally written by Seiki Guljo. It is a part of the Apache logging services, a project of the Apache Software Foundation. Log4j is one of several Java logging frameworks. Here you can see another architecture diagram of Log4j. Log4j is a layered architecture where each layer has a different object to perform different work. This architecture makes the design flexible and easy to implement. Two types of concerning objects available in Log4j framework: core objects. This is mandatory object framework. These are required to use the framework. Support object. These are optional objects of the framework. They always support core objects to perform an additional but important task. Core objects. Core objects include the following type of object. Core objects include following type of objects: loggers object, layout object, appender object. Loggers object, this is the top level logger. This is a top level layer logger that provides the logger object. The logger object is always responsible for capturing logging information, and they are also stored in the namespace hierarchy. Layout object. The layout layer provides objects which are used to format logging information in various styles. It provides support to Appender object before publishing logging information. Layout objects play an important role in publishing logging information in a way that this is a human readable and usability facility. Reusable facility. The ability to the Appender object, the ability to selectively enable or disable registration requests based on your register is only part of the image. Log4j allows registration requests to be printed in multiple destinations. In Log4j, an exit destination is called the appender. Support object. There are some other important objects in the Log4j framework that play a vital role in the logging framework. Some are level object, filter object, object renderer, log manager. Level object. This object defines the granularity and priority of any logging information. There are 7 levels of logging defined within the API: off, debug, error, info, fatal, and all. Filter object. This is used to analyze logging information and making further decisions to check whether that information should be logging or not. If logging information is passed to a particular appender object, all the filter objects compared with that appender need to approve the logging information before it can be distributed to the attached destination. Object renderer. This is specialized in a string representation of a different object passed to the logging framework. It is also used by the layout object to prepare final logging information. Log manager. Log manager will manage the logging framework. It is always responsible for reading the initial configuration parameter from a system-wide configuration file. Logging information is passed to logger object. Logger object, layout object, append object, and destination objects are core objects, and level object, log manager, filter object, and object renderer are support objects. And this is Java program. And logger object is connected to appender here, and here the layout object is connected to append object. Formatted info is passed from layout object to append object. Append object is connected to destination object. Log info is passed from append object to destination object. Now we are focusing on LoggerContext. The LoggerContext acts as the anchor point for the logging system. However, it is possible to have multiple active LoggerContext in an application depending on the circumstances. Here you can see interfaces lifecycle and lifecycle 2. With the lifecycle interface, all proper Java frameworks implement some sort of object lifecycle. In Log4j, the main interface for handling lifecycle context of an object is this one, lifecycle. An object first start in the lifecycle.state .initialized state by default to indicate the class has been loaded. From here, calling start method will change the state to lifecycle.state.starting. After successfully being started, the state is changed to lifecycle.state.started. When the stop is called, this goes into the lifecycle.state.stopping state. After successfully being stopped, this goes to the lifecycle.state.stopped state. In most circumstances, implementation classes should store their lifecycle.state in a volatile field and inside an atomic reference dependent on synchronization and concurrency requirements. In lifecycle 2, this extend the lifecycle interface. This interface should be merged with the super interface in 3.3 or 3.0. In the stop method blocks until all tasks have been completed execution after a shutdown request or timeout occurs, or the current thread is interrupted, whichever happens first. Here you can see a status of life cycle in This is in enum lifecycle.state. The status of a lifecycle like a LoggerContext here. Here you can see initializing object is in its initial state and not yet initialized. Initialized but not yet started. Starting, in the process of starting, and started, has started. Stopping is in progress, and stopped, has stopped. As an example, we can consider the interface LoggerContext. Anchor point for logging implementation. This is in package org.apache.login.log4j.spi. As an example too, we can consider interface LoggerContext. The LoggerContext is the anchor for the logging system. It maintains a list of all the loggers requested by applications and a reference to the configuration. The configuration will contain the configured loggers, appenders, filters, etc., and will be automatically updated whenever a reconfigure occurs. This class in the different package, the package this interface in a different package. The package is org.apache.login.log4j.co. Here you can see reconfigure log4j using configuration builder with the configurator. Here an alternative to a custom configuration factory. This is to configure with the configurator. Once the configuration object has been constructed, it can be passed to one of the configurator.initialize methods to set up the log4j configuration. Using configurator in this manner allows an application control over when the log4j is initialized. However, should any logging be attempted before configuration.initialized is called, then the default configuration will be used for those log events. Here you can see class configurator initializes and configure the logging system. This class provides the several ways to construct a logger context using the location of the configuration file, a context name, and various optional parameters. Here you can see the method public static LoggerContext initialize configuration. This initializes the logging context. This is the configuration here. This is in package org.apache.login.log4j.core.config. Here you can see a class log manager, the anchor point for the log4j logging system. The most common usage of this class is to obtain named logger. The method getLogger is provided as the most convenient way to obtain named logger based on the calling class name. This class also provides method for obtaining a named logger that use string.format string object style messages instead of the default type of parameterized messages. These are obtained through the getFormatterLogger class family of methods. Other service provider methods are given through the getContext. Here we consider getContext and getFactory family of methods. These methods are not normally useful for typical usage of log4j. Here you can see public static LoggerContext getContext boolean. This is the current context. This returns a LoggerContext. Here the parameter current context. If false, the current context appropriate for the caller of this method is returned. For example, in a web application, if the caller is the class in a web/lib webinfo/lib, then one LoggerContext may be returned. and if the caller is a class in the container's class path, then different LoggerContext may be returned. If true, then only a single LoggerContext will be returned. This class is in org.apache.logging.log4j package. Here you can see in this example here you can see the method in LoggerContext, the method public static LoggerContext get context boolean current context. This returns LoggerContext. Here the current context, if false, the logging context appropriate for the caller of this method is returned. For example, in a web application, if the caller is a class in web-info/lib, then one LoggerContext may be returned, and if the caller is a class in a container's class path, then a different LoggerContext may be returned. If true, then only a single LoggerContext will be returned. Here you can see logging separation in web applications. This is using Log4j 2 in web application. You can see these are context parameters here. Here Log4j context name, if is Log4j context selector named is true, Log4j context name must be specified or display name must be specified in web.xml. Otherwise application will fail to start with an exception. Log4j configuration should also be specified in this case and must be valid URL for the configuration file. However, this parameter is not required. By default, Log4j 2 uses servlet context name as the LoggerContext name and uses the standard pattern for locating Log4j configuration file. There are 3 context parameters that you can use to control this behavior. First is Log4j context selector named specified whether the context should be selected using the GNDI context selector. If the Log4j context selector named is not specified or is anything other than true, it is assumed to be false. If here the Log4j context selector named is not true, the Log4j configuration may optionally be specified and must be a valid URL or path to a configuration file or started with class path to denote a configuration file that can be found on the class path. Without this parameter, Log4j will use the standard mechanisms for locating the configuration file. When specifying these context parameters, you must specify them in a deployment descriptor web.xml, even in a servlet 3.0 or newer application. If you add them to the servlet context within a listener, Log4j will initialize before the context parameters are available, and they will have no effect. Here with the JNDI context selector, note that this case you must also set the Log4j context selector system property to org.apache.login.log4j.core.selector.jndi context selector. For security reasons, from Log4j 2.17.0, JNDI must be enabled by setting system property Log4j 2.enable JNDI context selector equal true. Here logging under logging separation, and then Java EE application. This is the Java server pages logging, and this is asynchronous request and threads. The interface Log4j web support. This is specified an interface for setting and clearing thread bound logger context in a Java EE web application. Also defines constant for context parameter and attribute names. In most cases, you will never need to use this directly because the Log4j filter handles this task automatically. However, in asynchronous operations, you should wrap the code that execute in separate threads. With set LoggerContext and clear LoggerContext. Here the method void set LoggerContext sets the LoggerContext so that code executing afterwards can easily and quickly access loggers via logmanager.setLogger. Here method void clear LoggerContext clears the LoggerContext set up in set LoggerContext, and this is in package org.apache.logging.log4j.web. This Log4j web support class. Sorry, Log4j web support interface. Log4j provides a simple mechanism for binding LoggerContext to asynchronous threads. In some special circumstances, the simplest way to do is to wrap the runnable instance that is passed to the async.context start async context start method. Here you can, as an example 8, you can see asynchronous request and thread in Java server pages in Java to EE applications in logging separation. Here the interface Log4j web cycle. This is specified an interface for initializing and deinitializing Log4j in in Java EE web application. The default and only implementation is Log4j web initialize IMPL. The initializer is based on an interface to improve testability. The methods are contained in a package private and sub interface because general application code should not have access to them. This is in package org.apache.logging.log4j.web. Here the method void set LoggerContext set the LoggerContext to so that the code executing afterwards can easily and quickly access loggers via log manager get logger, and here void clear LoggerContext method clears the LoggerContext setup in set LoggerContext. As an exception example, we can consider null point exception. If the specified name is null in the method public void set name string name in class LoggerContext in package org.apache.login.log4j.co. As another exception example, we can consider this occurred in the Apache in the environment with Apache Log4j 2.0.2. The null pointer exception in thread main java.lang.exception in initialize error caused by java.lang.class cast exception. org.apache.logging.slf4j LoggerContext cannot be cast to org.apache.logging.log4j core.LoggerContext, etc. Now we are focusing on configuration. Every LoggerContext has an active configuration. The configuration contains all the appenders, context-wide filters, LoggerConfigs, and contains the reference to the StrSubstitutor. During reconfiguration, two configuration objects will exist. Once all loggers have been redirected to the new configuration, the old configuration will be stopped and discarded. As an example, we can consider interface configuration. Interface that must be implemented to create a configuration. This is in package org.apache.logging.log4j.core.config. As an example 2, we can consider class abstract configuration, the base configuration. Many configuration implementations will extend this class. This in Apache. This is in package org.apache.logging.log4j.core.config. Here you can see initialize Log4j using configuration builder with the custom configuration factory. The interface configuration factory textend configuration interface for building logging configurations. This is in interface configuration builder textend configuration. This is a interface for building logging configuration. This is in package org.apache.logging.log4j.core.config.builder.api. Here the class configuration factory, the factory class for past configuration object from a configuration file. Configuration factory allows configuration implementation to be dynamically chosen in one of three ways. A system property named Log4j dot configuration factory can be set with the name of configuration factory to be used, or set configuration factory. Configuration factory can be called the instance of the configuration factory to be used. This must be called before any other calls to Log4j. A configuration factory implementation can be added to the class path and configured as a plugin in the configuration factory category. The old annotation should be used to configure the factory to be the first one inspected. This class is in package org.apache.logging.log4j.core.config. One way to programming configure Log4j2 is to create custom configuration factory that uses configuration builder here to create configuration. This example overrides get configuration methods to return configurations created by the configuration builder. This will cause the configuration to automatically hooked into Log4j when LoggerContext is created. In this example, because it specifies a supported file type asterisk, it will override any configuration files provided. Here in set, this is a configuration builder. Set configuration sets the name of the configuration. Here set status level sets the level of the status logger. Here in add adds a filter component. Here in this adds an Appender component. Here add the logger component. Here too. And here in the build, builds the configuration and optionally initialize it. Here as example 4, we can consider reconfigure Log4j using configuration builder with the configurator. Here the class configurator initializes and configure the logging system. This class provides several ways to construct LoggerContext using the location of configuration file, a context name, and various optional parameters. This is in package org.apache.login.log4j.core.config. Here you can see the configuration builder interface for building logging configurations. Here you can see configuration builder factory this provides methods to create configuration builders. Here the new configuration builder here returns a new default configuration builder to construct Log4j configurations. Here set status level sets the level of the status logger. Here set configuration name sets the name of the configuration. Here in the adds a filter component, and here adds an Appender component here. Here add the logger component. This is initialize Log4j by combining configuration file with programmatic configuration. Here the interface configuration interface that must be implemented to create a configuration here is in package org.apache.login.log4j.core.config. Here in get configuration returns the current configuration. As an example 6, we can consider arbiters. In some situations, it is desirable to have a single logging configuration that can be used in any deployment environment. For example, it may be necessary to have a different default logging level in production than in development. Another case might be where one type of appender is used when running natively, but another is used when deployed to a Docker container. One way to handle this, that is to use a tool such as Spring Cloud Config Server that can be environment aware and serve the different file for each environment. Another option is to include arbiters in the configuration. An arbiter is a Log4j plugin that has the job of determining whether other configuration elements should be included in a generated configuration. While all other core plugins are designed to execute as part of Log4j runtime logic, arbiters execute after the node tree has been constructed, but before the tree is converted to a configuration. An arbiter is a node itself, which is always removed from the node tree before the tree is processed. All an arbiter really does is provide a method that returns a Boolean result that determines whether the child nodes of the arbiter should remain in the configuration or be pruned. Arbiters may occur anywhere an element is allowed in the configuration. So an arbiter can encapsulate something as simple as a single property declaration or the whole set of appenders or loggers. Arbiters may also be nested, although arbiters that are descendant of another arbiter will only be evaluated if the ascender returns true. The child elements of an arbiter must be valid elements for whatever element is the parent of the arbiter. This example shows two arbiters configured that will include either a console appender or a list appender, depending on whether the value of environment system property is dev or production prod. As an example 7, we can consider automatic configuration. Log4j has the ability to automatically configure itself during initialization. When Log4j starts, it will locate all the configuration factory plugins and arrange them in weighted order from highest to lowest. As delivered, Log4j contains 4 configuration factory implementation, one for JSON, one for YAML, one for properties, and one for XML. Here Log4j will inspect the Log4j2.configuration step 1. Log4j will inspect the Log4j2.configuration file system property, and if set, will attempt to load the configuration using the configuration factory that matches the file extension. Note that this is not restricted to a location on the local file system and may contain a URL. This step 2. If no system property is set, the properties configuration factory will look for log4j2-test.properties in the class path. Step 3. If no such file is found in the YAML configuration factory, will look for log4j2-test.yaml or log4j2-test.yml in the class path. If no such file is found, the JSON configuration factory will look for log4j2-test.json or log4j2-test.jsn in the class path. Step 5. If no such file is found, the XML configuration factory will look for log4j2-test.xml in the class path. Step 6. If a test file cannot be located, the properties configuration factory will look for log4j2 properties on the class path. Step 6. If a properties file cannot be located, the YAML configuration factory will look for log4j2.yaml or log4j2.yml on the class path. Step 8. If a YAML file cannot be located in the JSON, the JSON configuration factory will look for log4j2.json or log4j2.jsn in the class path. Step 9. If a JSON file cannot be located in the XML configuration factory, if a JSON file cannot be located, the XML configuration factory will try to locate log4j2.xml on the class path. And step 10. If no configuration file could be located, the default configuration will be used. This will cause logging output to the console. As an example, we are considering configuration with XML. Log4j can be configured using two XML flavors, concise and strict. This is concise. The concise format makes configuration very easy, as element names match the component and they represent. However, it cannot be validated with XML schema. For example, the console appender is configured by declaring an XML element named console under its parent appender's element. However, element and attribute names are not case sensitive. In addition, attributes can either be specific as an XML attribute or as an element that has no attributes and has a text values. And this file represents the structure of an XML configuration. But note that the elements in italics below here represent the concise element names that would appear in their place. This is a strict XML. In addition to console XML format previously, Log4j allows configuration to be specified in a more normal XML manner that can be validated using XML schema. This is accomplished by replacing the friendly element names above here with their object type as shown here. For example, instead of the console appender being configured using an element named console, it is instead configured as appender element with type attribute containing console. Here you can see the configuration with JSON. In addition to XML, Log4j can be configured using JSON. The JSON format is very similar to concise XML format. Each key represents the name of the plugin. And the key value pairs associated with it are its attributes. Where key contains more than a simple value, it itself will be subordinate pattern. So subordinate plugin. Sorry. In this example, threshold filter, console, and pattern layout are all plugins, while the console plugin will be assigned a value of std out for its name attribute, and threshold filter will be assigned a level of debug. Note that in the routing appender, the root element has been declared as an array. This is valid because each array element will be a route component. Log4j, this is configuration with YAML. Log4j also supports using YAML for configuration files. The structure follows the same pattern as both XML and YAML configuration formats. You can see here. And additional runtime dependencies are required for using YAML configuration files. Here you can see configuration with properties. As of version 2.4, Log4j now supports configuration via properties files. Note that the property syntax is not the same as the syntax used in Log4j1. Like the XML and JSON configuration, properties configuration define the configuration in terms of plugins and attributes to the plugins. Prior to version 2.6, the properties configuration requires that you list the identifiers of the appenders, filters and loggers in a comma separated list in properties with with those names. Each of those components will then be expected to be defined in a set of properties that begin with component.identifier. Identifier does not have to match the name of the component being defined, but must uniquely identify the identify all attributes and subcomponents that are part of the component. If the list of identifiers is not present, the identifier must not contain each individual component must have a type attribute is specified that identifier is a component's plugin type. As of version 2.6, this list of identifiers is no longer required, as names are inferred upon the first usage. However, if you wish to use more complex identifier, you must still use the list. If the list is present, it will be used. Unlike base component, when creating subcomponents, you cannot specify an element containing a list of identifiers. Instead, you must define a wrapper element with its type. This example demonstrates how the shorthand is expanded when reading properties configuration. You can see the as an example 13, you can see the scripts. Log4j provides support for JSR 223 scripting languages to be used in some of its components. Log4j provides support for JSR 223 scripting languages to be used in some kind of its components. Any language that provides support for JSR 223 scripting engine may be used. A list of languages and bindings for them can be found in at the scripting engine website. However, some of the languages listed there, such as JavaScript, Groovy, and Bean Shell, directly support JSR 223 scripting framework and only require that the jars for that language be installed. As of Log4j 2.17.2, the languages to be supported must be specific as a comma-separated list in the log4j2.script.enable languages system property. The components that support using script to script do so by allowing script script file or script reference, script ref. Element to be configured on them. The script elements contains name for the script, the language of the script, and script text. The script element, the script file element contains the name of the script, its location, its language, its charsets, and whether the file should be washed for changes. The script ref element contains the name of the script that is defined in the script configuration element. The name of the script is used to store script along with the script, its script engine, so it can quickly be located each time the script need to be run. While the name is not configured, providing it will help in debugging problems when the script is running. The language must be provided on the script element must specify one of the language names appeared in the configuration status log as described, and in the languages, if the language is not specified on the script element, if the language is not specified on the script file element, the language will be determined by the file extension of the script path. If the monitoring is requested, it will only be enabled if the non-zero monitor interval is specified in the configuration element. This interval will be used to check for changes in the file. If the status attributes on the configuration element is set to debug, the list of script engines currently installed and their attributes will be listed. You can see here. Although some engines may say they are not thread safe, Log4j takes the steps to ensure that the script will run in a thread safe manner if the engine advertises that it is not thread safe. This is example for X-include. XML configuration file can include other files with X-include. Here's an example of log4j 2.xml file here that includes two other files. This is as an example 15, we can consider composite configuration. Log4j allows multiple configuration files to be used by specifying them as a list of comma separated paths on log4j.configuration file, or when using URLs by adding secondary configuration locations as query parameters named override. The merge logic can be controlled by specifying a class that implements the merge strategy interface on the log4j.merge strategy property. The default merge strategy will merge the files using following rules. Global configuration attributes, step 1, the global configuration attributes are aggregated with those in later configuration, replacing those in previous configuration with exceptions. High status will be used. The lowest monitor interval greater than 0 will be used. Packages are joined with comma. Step 2, properties from all configurations are aggregated. Duplicate properties replace those in previous configuration. Step 3, filters are aggregated under a composite filter if more than one filter is defined. Since filters are not named, duplicates may be present. Step 4. Scripts and script file references are aggregated. Duplicate definitions replace those in previous configurations. Step 5. Appenders are aggregated. Appenders with the same name are replaced by those in later configurations, including all the appenders subcomponents. Step 6. Loggers are all aggregated. Logger attributes are individually merged with duplicates being replaced by those in later configurations. Appender references on a logger are aggregated with duplicates being replaced by those in later configurations. Filters on a logger are aggregated under a composite filter if more than one filter is defined. Since filters are not named, duplicates may be present. Filters under appender references included or discarded depending on whether their parent appender reference is kept or discarded. As an example, we can consider class configuration exception. This exception is thrown when an error occurs reading from parsing, using or initializing the Log4j configuration. It is also thrown if an appender cannot be created based on the configuration provided. This is in the package org.apache.logging.log4j.core.config. As an error example, we can consider this occurred in the environment with JBoss 4.0.2 with Power Analyzer. Error passing error on line 273 and column 101. Error of the content of the element type log4j configuration must match render asterisk, append asterisk, category logger asterisk, root, category factory, and etc. Now we are considering StrSubstitutor. Substitutes variables with a string by values. As an example, we can consider class StrSubstitutor here. This is the main class we are referring actually. Substitutes variables within a string by values. This is in package org.apache.logging.log4j.core.lookup. The simplest example is to use this class to replace Java system properties, for example here and here. The method public static string replace system properties object here source. This is deprecated, and this replaces all the occurrences of variables in the given source object with their matching values from system properties. The typical usage of this class follows the following pattern. First, an instance is created and initialized with the map that contains values for available variables. Here, if the prefix and or suffix for variables should be used other than the default ones, the appropriate settings can be performed. After that, the replace method can be called, passing the source text for interpolation. In the return text, all the variable references, as long as their values are known, will be resolved. So this provide the quick brown fox jumped over the lazy dog. As an exception example, we can consider illegal So argument exception: if the prefix or suffix is null, in the method public string substitutor map string value map string prefix string suffix this is actually the this can be occurred in the constructor actually. This is a constructor here. This string substitutor is a constructor. As an error example, we can consider this occurred in the environment with Log4j2 and Apache Camel. Error invalid date format now :YYY mmdd-hh mmss using default java.lang.illegal argument exception illegal pattern character n and etc. Then org.apache.loging.log4j.co.lookup.str substitutor.resolve variable etc. Now we are focusing on StrLookup. Lookup a string key to a string value. The interface StrLookup lookup a string key to a string value. This is in package org.apache.logging.log4j.co.lookup. In this example here, the class map lookup, a map based lookup, and this is in package org.apache.logging.log4j.co.lookup, and the class interpolator. This is a proxies for proxies all other StrLookups. This is in package org.apache.login.log4j.co.lookup. Here in the constructor, construct an interpolator using a given StrLookup. And a list of packages to find lookups plugins. Here we are considering context map lookup. In this example, the application would store the current user's logging ID in the thread context map with the key logging ID. In context map lookup, the context map lookups allows application to store data in the Log4j thread context map and then retrieve the values in the Log4j configuration. During the initial configuration processing, the first $sign will be removed here. The pattern layout supports the interpolation with lookups and will then resolve the variable for each event. Note the pattern $sign the %sign x and then login ID would achieve the same result. As an example 4, we can consider Kubernetes lookups. The Kubernetes lookup can be used to look up attributes from Kubernetes environment for the container application is running in. Here account name, service account name, cluster name, the name of the cluster the application is deploying, container ID, the full ID assigned to the container, container name, the name assigned to the container, host, the name assigned to the host operating system, labels, all labels formatted in a list. Master URL, the URL used to access the API server. Namespace ID, the ID of the namespace the various components are located within. Namespace name, the namespace the various Kubernetes components are located within. Pod ID, the pod's ID IP number. And this pod's ID number, and this is pod IP number. Pod's name, the name of the pod. Image ID, the ID assigned to the content image. Image name, the name assigned to the content image. And as an exception example, we can consider this occurred in the Log4j with the environment with Log4j2 and JSON. JNDI lookup class is not available because this JRE does not support JNDI. JNDI string lookups will be available continuing configuration, and then java.lang classcast exception cannot cast org.apache.login.log4j.code.lookup JNDI lookup to org.apache.login.log4j.code.lookup.str Now we are focusing on logger. Loggers are created by calling logmanager.getLogger. The logger itself performs no direct actions. It simply has a name and it is associated with the LoggerConfig. It extends abstract logger and implements the required method. As the configuration is modified, loggers may become associated with the different LoggerConfig, thus causing their behavior to be modified. As an example, we can consider interface logger. This is the central interface in the Log4j package. Most logging operations except configurations are done through this interface. This is in package org.apache.login.log4j. As an example, we can consider this code segment. Here the class log manager, the anchor point for the Log4j logging system. The most common usage of this class is to obtain a named logger. The method getLogger is provided as the most convenient way to obtain a named logger based on the calling class name. This class also provide method for obtaining loggers that use string.format string objects style messages instead of the default type of parameterized messages. These are obtained through the getFormatter logger class family of methods. Other service provider methods are given through the getContext and getFactory family methods. These methods are not normally useful for typical usage of Log4j. The public static logger getLogger, this method here the public static logger getLogger string name. This returns the logger with the specified name of the class here, and here void, here the void info string message logs a message object with the info level. As an example 3, we can consider void this trace method, void trace marker, this trace method here. Here, since 2.4, methods have been added to the logger interface to support lambda expressions. New methods allow client code to lazily log messages without explicitly checking if the requested log level is enabled. With Java 8, you can see the effect with lambda expression here. Here with Java 8 style optimization, no need to explicitly check the log level, and here the lambda expression is not evaluated if the trace level is not enabled. As an example 4, you can see this logger configuration, and here and you can see the loggers here. This is especially with this configuration, all log events from com.foo.bar will be recorded, while only error events will be recorded from all other components. So here all the events from foo.com.bar logger were still written to the console. This is because the logger for com.foo.bar did not have any appenders configured, while its parent did. Oh, here there are appenders, sorry. And notice that without additivity part here, notice that the trace messages from foo.com.bar appear twice without this part. This is because the appender associated with the logger com.foo.bar is first used, which writes the first instance to the console. Next, the parent of foo.com.bar, which in this case the root logger is reference. This event is then passed to this appender, which is also write to the console, resulting second instance. This is known as additivity. While additivity can be quite convenient feature, in many cases this behavior is considered undesirable, so it is possible to disable it by setting the additivity attribute here, additivity attribute on the logger to false. Once this event reaches a logger with this additivity set to false, the event will not be passed to any of its parents loggers here, regardless of the additivity setting. As an example, we can consider this one occurred when migrating from the rules from Corticon 5.5.2 to 6.2 with the environment with the Corticon Studio Studio version 6.2 and with Windows. This is caused by java.lang.exception, java.lang.no class def found in org/apache log4j logger. This can be resolved. To resolve this, download log4j jar file and add it to Corticon 6.2 project as Corticon extension. The log4j jar file is removed since it is no longer used by Corticon. Corticon uses logback for logging. As an error example, we can consider this one caused by java.lang.no class def found error org/apache log4j logger in Java. Now we are focusing on LoggerConfig. LoggerConfig objects are created when loggers are declared in the logging configuration. The LoggerConfig contains a set of filters that must allow the log event to pass before it will be passed to any appenders. It contains the references to the set of appenders that should be used to process the event. Here you can see how log level filtering works. Log configs will be assigned to a log level. A set of built-in levels include all, trace, debug, info, warn, error, fatal, off. The log4j to also support custom log levels. Another mechanism for getting more granularity is to use markers instead. The off and all levels are not intended to be used on calls on the logging API. Specifying off in the configuration implies no logging events should match, while specifying all would mean all events match, including custom events. However, off can be used to logging API calls in special cases where the event should always be logged regardless of the configuration. However, it is generally recommended that a marker with the corresponding global marker filter should be used. Table here illustrate how level filtering works. In the table, the vertical headers shows the level of the log event, while horizontal headers shows the level associated with the appropriate LoggerConfig. The intersection identifies whether the log event would be allowed to pass for further processing, yes here, for further processing yes, or discarded no here. Here all means all events should be logged. Here trace means the fine-grained debug message, typically capturing the flow through the application. Here debug, a general debugging event. Info, an event for informational purposes. Warn, an event that might possibly lead to an error. Error, an error in the application, possibly recoverable. Fatal, a fatal error that will prevent the application from continuing. Off, no event will be logged. Here, if we configured log level to trace, all no, and other levels, other levels are yes. And if we set the configuration to debug, no for all and trace, and yes for other levels. And if we set the configuration to info, no for all, trace and debug, and yes for other levels. And if you set the configuration to 1, no for all, trace, debug, info, and for others, yes for others. And if we configure the LoggerConfig to error, and yes for error, fatal, and no for others. And if we configure the LoggerConfig to fatal, yes for fatal and no for others. And if we set the LoggerConfig to off, and yes to off, and no for other levels. As an example, we can consider class LoggerConfig, logger object that is created via configuration. This is in org.apache.login.log4j.core.config class or config package. Here you can see adds an appender and new logger configuration using that appender to the current configuration. Here LoggerConfig logger objects that is created via configuration. This is in class org.apache.login.log4j.core.config in package. Here the public static LoggerConfig create logger string additivity org.apache.login.log4j.level level and string logger name and string inclusion location, where the location should be passed to downstream, and appender refs array of appender names, and properties to pass to the logger is an array, and at plugin configuration config here, and filter. This method is deprecated in 2.7. Use create logger with the boolean value here, boolean for additivity. This add appender method adds an appender to the LoggerConfig. This is appender, and this is level, and this is filter. So here in the context, the add logger adds a logger, and this is the name, and this is the logger configuration, LoggerConfig. So here update loggers causes all loggers to be updated against the specified configuration. Here you can see LoggerConfig is configured using the logger element here, and loggers are here, and the logger element must have a name attribute specified. You will usually have a level attribute specified, and may also have additivity attribute specified. The level may be configured with one of trace, debug, info, warn, error, all, or off. If no level is specified, it will be default to error. The additivity attributes may be assigned to a value of true or false. If the attribute is omitted, the default value of the true will be used. Capturing location information, the class name, file name, method name, and line number of the caller can be slow. Log4j tries to optimize this by reducing the size of the stack that must be traversed to find the caller of the login method. It does this by determining if the component that might be accessed required location information. It can cause performance issues if a logger is configured at the level like trace or debug within the expectation that most logs will be filtered on an appender reference. So appender as log4j will calculate the location information even though the log event is going to be discarded. To disable this behavior, include location attributes can be set to false on the LoggerConfig. This will cause log4j to defer calculating the information until absolutely necessary. A LoggerConfig including root LoggerConfig can be configured with properties that will be added to the properties copied from the thread context map. These properties can be referred from appenders, filters, layout, etc. just as if they were part of thread context map. The properties can contain variables that will be resolved either when the configuration is passed or dynamically when each event is logged. A LoggerConfig may also be configured with one or more appender ref elements. Each appender referenced will be associated with the specified LoggerConfig. If multiple appenders are configured on the LoggerConfig, each of them be called when processing logging events. Every configuration must have a root logger. If one is not configured, the default root LoggerConfig, which has the level of error and has a console appender attached, will be used. The main differences between root logger and other loggers are: root logger does not have a name attribute. The root logger does not support the additivity attribute since it has no parent. Here the loggers root x and xyz each have a configured LoggerConfig with same name. The logger xy does not have a configured LoggerConfig with a matching name, so uses the configuration of LoggerConfig x, since that is the LoggerConfig whose name has the longest match to the start of the logger's name. As an error example, we can consider this one: C:\program files /java /jdk 1.0 8.0 _231 /bin /java.exe dlog4j1 dot compatibility equal true, trace status logger default configuration stopping root LoggerConfig, etc. This is occurred after log4j1 migration to log4j2 default configuration is being used. Now we are focusing on appender. Appenders are responsible for delivering log events to their destination. Every appender must implement the appender interface. Most appenders will extend abstract appender, which adds lifecycle and filterable support. Lifecycle allows components to finish initialization after configuration has completed and to perform cleanup during shutdown. Filterable allows the component to have filters attached to it which are evaluated during event processing. We can consider interface appender. Appends log events. An appender can contain a layout if applicable as well as an error handler. Typical appender implementations coordinate with an implementation of abstract manager to handle external resources such as streams, connections, and other shared state. As appenders are plugins, concrete implementations needed to be annotated with plugin and need to provide a static factory method annotated with plugin factory. This is in the package org.apache.login.log4j.co. As an example too, we can consider this code segment. Here you can consider here you can see interface appender component builder, the builder for constructing appender components. This is in the package org.apache.log4j.co.config.builder.api. Here with the configuration builder with a new appender string name and the string plugin name, this will returns a builder for creating appenders, appender component builder. With add attributes, it adds an boolean attribute. This is a key and this is value. With add here adds a layout to the appender component. Here the layout component builder as a parameter. Here in configuration builder is the method new layout returns a builder for creating layout. The string plugin here. Here the add attributes, add the boolean attributes. This is the key and again value here, the pattern. And this return the layout. Layout component builder. This method, the add method, adds a filter to the component. So this is the filter component builder here as a parameter. Here the new filter method returns a builder for creating filters. This is a filter component builder, and this is the plugin name. This is on match filter.result.deny, and this is on what happened on mismatch filter.result.neutral, and this is the attributes. Adds attribute boolean attributes. It's a key and this is the value. This will add the appender configure appender component builder to the configuration builder here. Here you can see in this code segment, this is a file appender. This is a file appender. This is in package org.apache.login.log4j.co.appender. In this code, this adds an appender and a new LoggerConfig using that appender to the current configuration. Here the create here the create appender. This is the string method. This is string file name, and then append, and this is the file name and path of the file, and this is true if the file should be appended to, false if it should be overwritten. Default is true here, and this is locking, true if the file should be locked, the default is false. This is name of the appender, and this is immediate flush, true if the content should be flushed on every write, false otherwise. This is ignore exceptions. If true, the default exceptions encountered when appending events are locked, otherwise they are propagated to the caller. Buffered IO, true if the IO should be buffered, false otherwise. Buffer size str, buffer size for the buffered IO. Layout, the layout used to format the event. And the filter, the filter if any to use, and advertise, true if the appender configuration should be advertised, false otherwise. Advertise URI, advertise URI which can be used to retrieve the file contents and the configuration. And this method is deprecated. You can use new builder method instead. The start method make the filters available for use, and this will add the appender, and this is appender appender reference. Here this create appender reference, this will create an appender reference. This is ref, the name of the appender, and this is the level to filter against, and this is the filters to use. And this is LoggerConfig, logger object that is created via configuration. And this is create logger here. This will create the logger here, and this is additivity. This is deprecated and use the create logger with boolean method here. And this is log level, and this is logger name. Include location, refs here, properties, configuration, and filter. This is add in the log configuration, add appender. This will add an appender to the logger config. This is appender and level and filter. This is add logger, and this is logger name and the logger config here, and this will update loggers in the context. Here you can see writer appender appends log events to a writer. This is in package org.apache.login.log4j.co.appender. So for any given writer, like a print writer, you tell Log4j to append events to that writer by creating writer appender and updating the Log4j configuration. This is create appender creates a writer appender. This is the layout and filter the target writer, and this is follow. If this is name of the appender, and this is follow, and if true will follow the changes to the underlying output stream. Use false as a default here, and this is ignore. True, default exception encountered when appending events are logged. Otherwise they are propagated to the caller. In the start, make the filter available for use, and this will add the appended, and this is updating the logger. This is a typical console appender configuration. As one might expect, the console appender writes its output to either system.out or system.error, with system.out being the default target. The layout must be provided to format the log event. Here the parameter name, the name of the appender. This is the target string, either system_out or system_error. The default is system_out. File appender. The file appender is an output stream appender that writes to the file named in the file name parameter. File appender uses a file manager which extend output stream manager to actually perform the file I/O. The while file appenders from different configurations cannot be shared, the file managers can be if the manager is accessible. For example, two web applications in a servlet container can have their own configuration and safely write to the same file if Log4j is in a class loader that is common to both of them. Here the name is the name of the adapter, also name of the appender, and here the file name, the name of the file to write to. If the file or any of its parent directories does not exist, they will be created. As an example 7, we can consider JDBC appender. The JDBC appender writes log files the writes log events to a relational database table using the standard JDBC. It can be configured to obtain JDBC connections using JNDI data source or a custom factory method. The JDBC appender configured with data source requires a JNDI support. So as of release 2.17.1, this appender will not function unless log4j2.enable JNDI JDBC equal true is configured as a system property or environment variable. Here the parameter name is required and the name of the appender. Here the table name required, the name of the database table to insert log events into. The nested element data source uses JNDI. Do not share this connection with other clients. And here the JNDI name is required and parameter, the full prefix JNDI name that javax.sql.data source is bound to, such as here the data source must be backed by a connection pool, otherwise logging will be very slow. And you can see column name and is event timestamp, column name, pattern, etc. As an exception example, we can consider appender logging exception, class appender logging exception, thrown from an appender when a log event could not be written. Appender should not throw an exception if an error occurs that does not stop the event from being successfully written. Those types of errors should be logged using the status logger. Appender should only throw exceptions when an error prevents an event from being written. Appenders must throw an exception in this case so that error handling features like the failover appender work properly. We can, as an error example, we can consider this occurred in the environment with Tomcat. Error could not find the value for key.log4j.appender.error, could not instantiate the appender name error, could not find the value for log4 j.appender.error and could not instate appender.error. No appenders could be found for logger, etc. Now we are focusing on filter. Filters allow log events to be evaluated to determine if or how they should be published. A filter will be called on one of its filter methods and will return a result which is an enum that has one of three values: accept, deny, or neutral. We can consider interface filter. Interface that must be implemented to allow custom event filtering. It is highly recommended that applications make use of the filters provided with its implementation before creating their own. This is in Apache. This is in package org.apache.logging.log4j.core. The method new filter filter command builder, new filter, plugin stream plugin name, filter dot result on match here, and filter dot result mismatch here. In the add attributes, adds a boolean attribute, key and value here, and this returns filter component builder, the new filter method. and this is added then to the builder, to the component build, to the configuration builder here. As an example 3, we can you can see here the class threshold filter. This filter returns the on-match result if the level in the log event is the same or more specific than the configured level in the on mismatch value otherwise. For example, if the threshold filter is configured with the level error, the log event contains the level debug, then on mismatch value will be returned since error events are more specific than debug. The default level is error. This is in package org.apache.login.log4j.co.filter. This is method creates create filter, public static threshold filter create filter, creates a threshold filter. This is log level and the match, the action to take on match and the action to take on mismatch. The burst filter. The burst filter provides a mechanism to control the rate at which the log events are processed by silently discarding events after the maximum limit has been reached. The configuration containing the burst filter might look like this, and here the level is a string and the level of the message to be filtered. Anything at or below this level will be filtered out of max burst has been exceeded. The default is 1, meaning any messages that are higher than the 1 will be logged regardless of the size of the burst. And rate, this is a float value, and the average number of events per second to allow. The max burst, the integer, and the maximum number of events that can occur before events are filtered for exceeding the average rate. The default is 10 times the rate. Log4j, this is configuring filters. Log4j allows a filter to be specified in any of 4 places. One, at the same level as the appenders, loggers, and property elements. These filters can accept or reject events before they have been passed to a LoggerConfig. In the logger element, number 2, in a logger element, these filters can accept or reject events for specific loggers. Number 3, in an appender element, these filters can prevent or cause events to be processed by the appender. And number 4, in an appender reference element, these filters can be these filters are used to determine if a logger should route the event to an appender. Although only a single filter element can be configured, that element may be filters element which represent the composite filter. The filters element allows any number of filter elements to be configured within it. This example shows how multiple filters can be configured on a console Appender. As an error example, we can consider this error occurred in the environment with OpenJDK version 11.0.10 and OpenJDK runtime environment Correcto 11.0.10.9.1 and OpenJDK 64-bit server VM Correcto 10.9.1 users /users etc. and error duplicate class org.apache.login.log4j.core.filter.burst filter etc. Now we are considering a layout. An Appender uses a layout to format a log event into a form that meets the need of whatever will be consuming the log event. In Log4j 1.x and logback layouts were expected to transform an event into a string. In Log4j 2 layouts return a byte array. This allows the result of the layout to be useful in many more types of appenders. However, this means you need to configure most layouts within a charset to ensure the byte array contains correct values. Interface layout t-extend serializable lays out a log event in different formats. Formats are byte array and implementer of serializable like byte array, string, log event. Since 2.6, layout can encode a log event directly to a byte buffer destination without creating temporarily intermediary objects. This is in package org.apache.login.log4j.core. Here you can see the component builder new layout method layout component builder new layout string plugin name. This returns a builder for creating layouts and the attribute key and value is here, and it is added to the Appender builder. Here the class pattern layout, a flexible layout configurable with pattern string. The method public static pattern layout create default layout configuration creates a pattern layout with using the default options and given configuration. These options include UTF -8, the default conversion pattern, exceptions being written and with NC escape codes. This is this class is in the package org.apache.login.log4j.core.layout, and here the layout is passed to the method create appender here. Here CSV layouts. This layout creates a comma separated value CSV records and required Apache common CSV. And the method debug here, string message and object here, the parameter to the message, one parameter to the message, two parameter to the message, message 0, 1, 2 here. The CSV layout can be used in two ways. First, using CSV parameter layout to log event parameters to create custom database, usually to a logger and file appender uniquely configured for this purpose. Secondly, using CSV log event layout to log events to create a database and as an alternative to using full DBMS or using the JDBC driver that supports the CSV file. The CSV parameter layout converts an events parameter into a CSV record, ignoring message. Logging as a CSV events look like this here. This produces a CSV record with the following field: the time nanos, and time millis, and level, thread ID, thread name, thread priority, and formatted message, and the logger FQCN, and logger name and marker, thrown proxy source, source, and context map and context stack. And additional runtime dependencies are required for using CSV layouts. You can as an example 5, you can consider as here to send a Greylog 2.x server with UDP. Guelph layout lays out events in Greylog extended log format, Guelph 1.1. This layout compresses JSON to gzip and zlib. The compression type: if a log event data is larger than 1024 bytes, the compress threshold. This layout does not implement chunking. Here the parameter name host string and the value of the host property optional default to local hostname here. This is the one. And compression type can be a gzip, llib, or off. Compression to use optional default to gzip. Here zlib. And compression threshold, this is integer, and compressed if data is larger than this number of bytes, optional default to 1024. As an example, see configure as follows to use data pattern and time zone. HTML layout: generate HTML page and adds each log event to a row in a table. So here date pattern, parameter name, and this type string, and the date format for logging event. The default is JVM underscore elapse underscore time, which output the milliseconds since JVM is started. This is here. This is ISO 8601, and time zone. This is string and the time zone ID of the logging event. Here you can see JSON layout appends a series of JSON events as a string serialized as bytes. Here a pattern layout, a flexible layout configurable with the pattern string. The goal of this class is to format log event and return the result, format of the result depending on the conversion pattern. Here this example shows how to filter out classes from unimportant packages in stack traces. The conversion pattern is closely related to the conversion pattern of the printf function in C. A conversion pattern is composed of literal text and format control expressions called conversion specifiers. Each conversion specifier starts with the percentage sign and followed by optional format modifiers and conversion character. The conversion character specifies the type of the data category, for example, category, priority, date, name. The format modifiers control such things as field width, padding left, right justification. Here the pattern, the parameter name pattern is a string. A composite pattern is string of one or more conversation patterns from the table here. Patterns cannot be specified within a pattern selector. Here the m percentage sign of m output the message, output the application supplied message associated with the logging event. This $sign xex, same as the $sign throwable conversion word, but also include class packaging information. Here percentage n outputs the platform dependent line separator character or characters. As an example 9, we are considering XML layout appends a series of event element as defined in the log4j.dtd. This is to include any custom field in the output. Use this syntax. In YAML layout appends a series of YAML events as strings serialized as bytes. To include custom fields in the output, you can use this for this syntax here. Here you can see JSON layout appends a series of JSON event as a string serialized as byte. Here you can see the log events follows this pattern in JSON. With XML layout appends a series of event element as defined in the log4j.dtt. Well-formed XML document follows this pattern. With YAML layout appends a series of YAML events as strings serialized as bytes. A YAML log event follows this pattern. As an exception example occurred in the environment with AnyPoint Studio, we can consider this could not create plugin of type class org.apache.login.log4j.core.layout.pattern layout for element pattern layout, java.land.nullPoint exception, etc. As an error example, we can consider this occurred in the environment Oracle Data Integrator version 12.2.1.4.0 to 12.1.2.1.4.2006-18. javaland.no class def found error, org.apache.log4j.layout error when executing ODI to LC mapping using Hyperion S-base KM. This is end of my presentation. Thank you very much for watching.